statistics is critical for biology, I think, to enable people to discriminate the biological signal that's interesting against the background of variation. So it allows you to determine how likely it is that your signal isn't just something that was observed by chance, because you can compare it to the underlying variation. And of course, statistics is important for exploring in data sets as well, to see, to generate new hypotheses for future experiments. Mathematical modeling in general makes it possible to explore likely and possible future outcomes under the, when you have partial knowledge of a system and you'd like to explore what might be possible in that system. Well, so I work in disease epidemiology, and mathematical modeling is important at several scales. It might be one of the smaller scales where it's useful is in an individual farmer's field. If they're working with a problem with a particular pathogen, disease forecasting models can be used to give them information about when they might need to apply a pesticide if they rely on pesticides for disease management, or when they might want to apply a cultural practice, and when they might be able to avoid applying a pesticide because based on meteorological variables that would go into the model, there's not really enough of a disease risk to motivate using a pesticide. At larger scales, it's interesting to use disease forecasting models to understand, for example, under climate change scenarios, which diseases would become more of a problem, which diseases might become less of a problem, so that people can plan ahead for where they would need to invest effort for plant breeding, say, to develop new types of resistance. Well, mathematics makes it possible to, especially in the context of climate change analyses, to explore what we think are the likely outcomes under climate change scenarios and what are the possible outcomes, so that people can try to prepare for both. That's one example where we're not able necessarily to do the type of experiments at the scale that would be necessary to really do an empirical experiment, but we can do mathematical experiments to allow us to see what the range of different outcomes are and how likely the different outcomes might be. Well, I think it's critical whenever there's variation and uncertainty to use statistics and other mathematical tools to separate out the signal in the background of noise, and then also often the variation itself is very interesting. So to be able to use mathematical tools to model the variation in biological systems, since they are so variable.